Welcome back. We're on the third installment of the Chemistry for Kids video series, and in this lesson today we're going to learn about matter and measurement. Specifically, we're going to touch on more about the measurement on my part, and Professor Boron, my colleague here, is going to touch a little bit on the matter portion of the chemistry series. So
right, M&M, keep that in mind.
M&M.
So matter, just some basic things. We're going to talk about, 3 states. Most people know about that, but we'll get into that.
There's technically a 4th state as well, but
well, actually, there's 5.
So measurements, we're going to touch a little bit on like the centimeters, the decimeters, definitely the football fields, and
just how bad the American system is.
That's not why I brought it up.
Oh, well, okay.
And that is it. Onto the lab station.
Right.
It is a fascinating journey, this path of knowledge, and the vehicle we ride is a science called chemistry.
Here we go!
Alright, so you ready to do this?
I think so. I know it's a suit, by the way.
Thanks a lot, yeah.
This costs a lot of money.
Yeah, it did cost a lot of money.
Well, I mean, you're working this job, so I'm assuming you don't make too much.
No, I mean, there's other stuff.
Oh, there is? Suiting up. All right, welcome back. Professor Boron.
Yep.
Right here in my hand, what do I have in my hand right here?
It's a meter stick.
Yes, exactly right. This meter stick can go up to 100 centimeters, and it's pretty versatile in what it can do. It can measure distance from somewhere, but concerning our teachings today, this is going to be about measuring properties of matter.
Yeah, so you could measure the length, simple.
Yeah, measure the distance from me to Boron. It's about exactly 100 centimeters. Wow.
Look at that.
We also have a balancing thing. It's somewhere near.
Mass scale?
A mass scale.
Oh, but we don't have those,
Mass
do we?
scale.
Wait, why do we get rid of those?
Budgeting.
Budgeting?
Yeah. Let's continue on. Okay, so here there's more equipment like this, but they vary from size. This can be much smaller. There's instances where this flask right here can go up to at least 10 milliliters. But for mainly what you want to use these for is just to measure differences in measurement. So if I put water in here, I measure it with the eye and go, yep, that is above.
Well, don't forget, you gotta put it on the surface and you gotta see it at eye level, right?
Absolutely. I totally
You forgot to mention that.
Thank you so much.
So you would just look at it from, that's the setup first, but obviously you would want to look at it. So it seems like with almost no effort at all, you somehow got exactly 350 milliliters.
Oh, I did?
How did he do that?
Of course I did. Yeah.
What the heck?
I don't know.
Anyway, I guess just move on. Yeah. So then we would have this giant what's the name?
I think it's another flask.
Oh, it's another flask.
Everything here is a flask, but this
right.
is a large flask.
This is a graduated cylinder. Don't forget that.
Absolutely. Yeah. Well,
This is also a handy tool that usually is used. This or a beaker is what we mainly would measure. But this and these 2 flasks can also be handy depending on their situation.
Yeah, and finally this is the purette. This device. You put some sort of substance in there, any sort of solution, and what you do is you want to move this little lever here, and that'll continuously drop streams of the solution that you want. You can drop drops, or you can just drop a continuous stream. And this is mostly used for titration, but you don't even know that now.
And obviously, this is for volume. So, you don't get any ideas, just it's for volume, but we'll talk about that in our matter section of the video. Master Chemist, you should be careful with that.
What?
I said you should just be careful with the meter stick.
Oh, well, it is 100 centimeters long, so I My apologies.
Okay. Anyway.
So yeah. So there's certain prefixes that people should use when measuring whatever they want to measure, including distance. So the first thing we want to know is that kilo is equal to 10 to the third, meaning that that's about 1,000. So if I want to mention something like the distance from a city to a city, then it's going to be in kilos, because that's kilometers, yeah. So for the third one, we have hecto. It's primarily not really used that much, but you know, it's just there, just to be there. Deca, also not used as much, because why would you use deca when you can measure in like certain in kilos? Because you've seen like those sorts of measurements where they're like 0.73 kilos. Instead, you could say hecto, but no one really does. Units. This is the unit of measurement, so we measure it based off that, and we go from there. Decimeters. That's like close to a centimeter. It's not as often as we use deci, but it's pretty relevant. And centimeters, we all use that.
For example, the meter stick that's on the floor.
Absolutely, yeah. The meter stick. And finally, we have the millimeter. Millimeter.
Millimeter.
Yeah, millimeter, which is also used a ton when we want to measure things like, because we can go as small as we want. We can go even smaller than this, but these are the primary units that we use to determine like the amount of what something has.
Yeah. So like in certain cases, you have things like nanometers, which could be, that's approximately a millionth of a meter, or picometers, which is a billionth. But for the most part, you're not going to use something like that. What these are usually referenced to would be what's called SI units, which is just basically the standard units we would use when it comes to measurement. And a very important one that I'd like to talk about, if you don't mind, is what's known as the mole. So it's not typically, it's not a mole that you'll find in a brownie. It's not star-nosed or anything, or a blemish on your skin. But what this is, it has to do with this guy called, he goes by the name Avogadro. And what he did is that he found that when it comes to gases, the volume is often proportional with the amount of atoms there are. So he came up with what's called Avogadro's constant. So 1 mole in this instance equals to 6.022 times 10 to the 23rd particles / atoms in 1 mole. So usually how you would get these moles, let's say you had, 1 gram of hydrogen, right? So whatever, like the grams. Then on the bottom, you would have its molecular mass. So with hydrogen, the molecular mass would be 1, 0, 2. And usually, whatever this equals, that would be how many moles you have, and with that you can have a reference of how many particles are in it. So some of you might be concerned, I suppose, with what the heck does this mean? Master Chemist used it here, but I don't think he really described it correctly. He mentioned this was 1,000, right? But he didn't say it was 1,000 meters. But typically, I'm sure some of you have worked with exponents, so you would know what this means. But typically, we would use something like this, which is called a scientific notation. So we would have a number. Usually, what you would do is it would be between 1 and 10, or around there. And it would be something like times to the 10 to the 23rd. So when you're talking about stuff like this is usually when you want to describe very large or very minuscule amounts of certain substances. So the negative third would be, a 0.0001. So in that instance, so it'd be like 1,000th of a meter, and just like with the centimeter, it'd be 100th. That's how you would further elaborate on that.
Another thing is, this is 0.01. So, but when we look at a meter stick, we look at the centimeters here, but the values are just 1. I think, do you want to explain how that is?
About what?
About how meter signatures, centimeters is the value of 1, but here there's a value of 0.01.
Well, it's probably because it's in reference to the meters, as I've already said.
Okay. Yeah.
So it would be, 0.01 of a meter. And then this would be 0.001. I believe I said 000. That's a mistake.
That's a mistake. First of all.
I can't believe I made a mistake.
Okay.
Anyway, I think we'll wrap it up there.
Thank you for coming and clicking on this video. Stick around for the viewer submitted responses.
Right. And I believe the next video is going to be about atomic structure. But, you can't forget, we have the matter portion of this video. So we can't really sign off yet, can we?
I don't think so. Matter unit?
Excuse me? No. This is matter and measurement. Remember M and M?
Absolutely.
You completely forgot the matter part. What happened?
Oh, solid, liquid, gas?
Well, there's more to that.
Okay.
There's plenty more. What are you talking about?
Solid, liquid, gas. That's all you guys
Yeah,
need.
so we're going to talk about that in a minute. We need to work things out right now.
Okay, so, wow.
Okay, welcome back, guys. We're back. Now we're going to talk about matter. Sorry about the disturbance.
Careful planning, next time. It's
Yeah, but anyway, so I would like to talk about matter in general. I think most people would agree. Most common phases of matter that, or the states of matter that we typically talk about is, solid, liquid, and gas. So what I have here is a graph that actually talks about, like, the substances themselves, the states, while also talking about or demonstrating the different states and the changes that actually occur within them all. So, as you can see, as heat is added towards something like a solid, and as temperature increases, of course, you're gonna have the transition period here from the solid to the liquid, which typically you would call melting. But when you're going back to the solid from liquids, that would be then being called like it's freezing, right? You're freezing an ice cube, so it becomes an ice cube. But anyway. And when it comes to liquids to gases, that's typically called evaporating, and then from gas to liquid, that's condensation. There are instances where solids can actually go straight and become gases. That would be called sublimation. That is something that you would want to remember because that is often a word that is used in context with the course. So you should know what it means.
So what in the real world goes through sublimation?
Oh, so what? Okay, so that would be like carbon dioxide. Like ice cubes?
Dry ice?
Dry ice, of course. Yes, dry ice. That's typically a notable example that you would have when it comes to sublimation. It goes straight from solid to carbon dioxide. Simple as that, right? Mm-hmm. So further delving into that, when it comes to matter and the changes themselves, there's these things. They're typically into two categories. You have physical changes and you have chemical changes. Physical changes are usually changes that are observed with the senses, but have nothing to do with, like that. Right? That's a physical change because the substance itself, like the pencil, it is still a pencil, but there is an observable physical change that happened to it. It's broken in half. But something like a chemical change is something to do with actually changing the substance itself. One example that most people use would be burning paper. You can really use the charred ashes of that previously called paper and turn it back into paper. In that instance, that would involve chemical reactions. You would have to somehow reverse that, which that would be interesting.
It's almost irreversible.
Almost.
Yeah.
Right. Anyway, so away from that, with classifying different types of matter. You can start with elements, which are typically homogeneous, all the same thing. They're made of, like elements, right? They're all made of the same particular atom. So if you have hydrogen, whatever amount you have in there, it's all hydrogen atoms, and it's a pure substance. It's homogeneous. There's nothing else there, right? With compounds, you usually get those through chemical means, right? So this could be, an example would be
H2O.
H2O works. Water is a good compound. It's good for you. You can swim, you can drink, you can live. Write it down. So how you would notate that would be through formulas like this. The elements, you just use symbols. So with the hydrogen, of course, you just use a capital H. But with compounds, you would typically use formulas like this, right? And
So for something like an element, you have something like just He by itself.
yeah, helium, yeah, that works.
That works. Is that a mixture?
And then mixtures, these are typically consisted of different, like a plethora of particles. You know, you'd have different things. So you could have water, you could have, a funny example could be something like a pizza. You have all these crazy different toppings. You have pepperoni, you have sausage, it's not a pure substance. It can be homogeneous, it can be made out of the same when it comes to solution, but it is possible for it to be not so quite. But also, these are usually acquired through physical means. So that would be, you know, like the active physical action that you have when mixing those together, rather than the chemical methods that you would use to get compounds.
So if you mix something like water and something
with like
sodium, for example, right? So if you mix water and sodium,
well, right, but Master Chemist, you know what happens with water and sodium, right?
yeah, but moving on though. Moving on. Do you want to say something else?
I think that's a good wrap up.
Okay.
Don't do this, by the way. You do not want to mix water and sodium. Please don't. You just bad.
It's not like living at sodium then.
What?
Sodium is very hard to get, so we don't even have it.
But if you can somehow get it, just don't do that, please.
Okay. But that's for another episode. Thank you so much for watching. Stick around for some viewer submitted videos as always.
All right.
And as always, Master Chemist.
And this is us
Peace.
for real signing off this time.
For real.
The next time you'll see us is actually talking about atomic structure and theory. Cool? Good? Farewell. Bye.
Peace. Welcome back to the Chemistry Corner. This is the second installment of our viewer submitted question series, and let's open up the archives to see if there's more questions. There is. The first question is from Ivan Den One Sovish, and he says, Professor Boron, more like a boring moron. Okay. The second question is from Matt Damon, and he says, so I'm working on this movie called The Martian, and I was wondering if this has to do with botany in space. I have no experience with space. I'm not sure if you can grow stuff out in outer space. That's not a thing. I don't think you can do that. Final question is from Tunda AAA, and he asks, I like the addition of meters as a unit of measurement, but I like my yards and my feet. Can I keep those as well? No unit of measurement is wrong, but it is mostly preferred to use meters and liters and stuff like that. You don't want to use this feet and inches because like the rest of the world doesn't use that. We only use that in the United States. So hope that helps. And that's it. That's all I had. And okay, this is the second installment. Thank you all for watching. And Master Chemist, peace.
Finally. All right. What the heck? Oh, jeez. Why God?